So we've just got through talking about functions, trigonometric inverse functions, and evaluating these inverse trigonometric functions. And so now we want to look at solving equations with trigonometric functions. So we're going to be solving these equations. These equations that we're going to start with this section only has one trigonometric function. And so let's look at an example. Let me kind of just walk you through on how to do this. So let's say that you had 1 minus cosine of theta is equal to 1/2. And so it wants us to solve this equation, and it wants us to find all the values of theta between 0 and 2 pi. So we have 0 is less than or equal to theta is less than or equal to 2 pi. Okay, so when we're dealing with these trigonometric equations, if it does not have the inverse function in here, we have to look at all the values of theta that would give us our answer. So when we were dealing just a moment ago with our inverse trigonometric functions, we had to limit that range in between whatever the range was for that inverse trigonometric function. But we're not doing that in this case because this is cosine theta in here. So when we're solving these trigonometric equations, and there's only one trig function in there, isolate that trig function. So let's get cosine theta by itself, and we can do that by subtracting 1 on both sides. So we have negative cosine of theta is equal to subtracting 1 from 1/2. That would get me negative 1/2. And let's make this positive cosine of theta. So cosine of theta is equal to 1/2. And so you're thinking about all the angles that would make cosine theta 1/2. And we know that cosine theta is positive, our answer is positive, in the first and the fourth quadrant. So let's first think about the first quadrant. So I know 60 degrees or pi thirds would get me back positive 1/2. So theta is going to equal pi thirds. And then in the fourth quadrant, well, we want this between 0 and 2 pi, so it doesn't have any of the negative angles in there. And so if we look at this fourth quadrant, and our reference angle in here is pi thirds. We want to know what is that angle that got us around to that terminal side. And we can figure that out by looking at a whole circle, which is 2 pi, minus that little itty bit of pi thirds to find that angle. So that's 6 pi thirds minus 1 pi thirds, getting a common denominator. So that would have to be 5 pi thirds. So theta is pi thirds, and 5 pi thirds would be the two angles between 0 and 2 pi that would give us cosine of that angle is 1/2. So let's pull another one. Let's say, I don't know. How about tangent squared theta? This is equal to 1/3. Again, we want to find all the values of theta between 0 and 2 pi that would satisfy that equation. So I have tangent squared theta, I want tangent theta. And so I can use the fact that have a perfect square on that one side equal to the other side, we could take the square root of both sides of that equation to get that as a single tangent theta. But if we take the square root of both sides, don't forget we need to put plus or minus on the one side. So this is the same thing as the square root of tangent squared theta equals plus or minus the square root of 1/3. And so tangent theta is equal to plus or minus. Well, if we have a square root of a fraction, we can look at it as the square root of the numerator over the square root of the denominator. Square root of 1 is 1 all over square root of 3. Let's rationalize our denominator real quick. And so we can multiply this by root 3 over root 3. So we're looking at when is tangent theta equal to plus or minus root 3 over 3. So thinking about the first quadrant, this is the one that had all the 3s, so I know that that was 30 degrees. Tangent of 30 degrees or tangent of pi 6 has the root 3 over 3. So theta for the first quadrant is pi 6. But tangent in the second quadrant, that would give me a negative value. So pi 6, that reference angle is pi 6 in the second quadrant. And so the angle that would get us up to that would be pi minus pi 6, or 6 pi 6 minus pi 6, which is 5 pi 6. So 5 pi 6 also works. That would give us a negative root 3 over 3. Let's look at the angle in the third quadrant. So our reference angle again is pi 6, but it's in the third quadrant. So to get that full angle from the standard position down here to this terminal side, I'd have to take pi plus pi 6. So pi, I can think of as 6 pi 6 plus 1 pi 6 is 7 pi 6. And then the last angle, which would give us a negative root 3 over 3, is in the fourth quadrant. Again, reference angle is pi 6 there. So thinking of 2 pi minus pi 6. So 2 pi, getting a common denominator, is 12 pi 6. 12 pi 6 minus 1 pi 6. That would be a 11 pi 6. So there's 4 angles that we could take tangent squared of those angles and get back 1/3. And there would have been an infinite number of angles, but we wanted all the angles but just between 0 and 2 pi. So when you're doing the homework or a test question, look to see, do they limit what theta is, or do they ask us for all of the solutions? So looking at our equation, we have 4 sine theta plus 3 root 3 is equal to root 3. And we want to solve this for theta, find all the exact values of theta between 0 and 2 pi. So again, if there's a single trigonometric function, you're going to isolate that on the one side of the equation. So we want to get rid of that root 3. So we could subtract 3 root 3 on both sides. So we get 4 sine theta. Because these both have a radical of √3, we can add or subtract them. So 1 √3 minus 3 √3, that's the same thing as a -2 √3. We want sine theta by itself, so we could divide both sides by 4. So we get sine theta is equal to, this reduces down 2 and 4, and so this is -√3 all over 2. So before I think about what value or what angle of sine gives me back -√3 over 2, I like to think of what angle gives me back +√3 over 2. And then I can use that angle as my reference angle in the quadrants where sine is negative. And so I know 60 degrees, which is pi-thirds, sine of 60 or sine of pi-thirds is equal to -√3 over 2. And so I know my reference angle is equal to pi-thirds. And so again, knowing that sine is negative in this third quadrant. Oops. So I want to figure out what is that angle that would get me down to the terminal side, starting at the standard position. So pi plus pi-thirds, or 3 pi-thirds plus pi-thirds, theta is going to equal 4 pi-thirds. And then I also know that sine is negative in that fourth quadrant. So reference angle of pi-thirds in the fourth quadrant. So that angle, starting at the initial side to our terminal side, or from standard position. So that's 2 pi minus pi-thirds. I need a common denominator. So 6 pi-thirds minus 1 pi-third is 5 pi-thirds. So there's 2 values of theta. That would give me back sine of those angles is -√3 over 2, which are the solutions to our original equation. So our next example, cosine of 2 theta equals -1/2. So our trigonometric function is isolated on the one side. The problem is that this argument is 2 theta and it's not just theta. And so we need to be careful if that argument is not just that variable, in our case, theta. So we need to do some manipulation. And so maybe we can say, well, let A equal 2 theta. And so we can rewrite this. This is the same thing as cosine of A equals -1/2. So we're thinking about cosine of what angle gives me -1/2. Well, cosine of pi-thirds is +1/2. So I know my reference angle is pi-thirds. So I know that cosine is negative in quadrant 2. And if that reference angle is pi-thirds, then pi minus pi thirds. So 3 pi thirds minus pi thirds is 2 pi thirds. So A can equal 2 pi thirds. But cosine is also negative in that third quadrant. And so pi plus pi thirds, 3 pi thirds plus pi thirds is 4 pi thirds. Would also give us back negative 1/2. So we don't want A, we want theta. So we're going to say, well, A is equal to 2 theta. So we're looking at 2 theta equal to 2 pi thirds. The problem is, remember that argument, if that argument had a coefficient in front of that angle, that theta, then that could have shrunk the period, or it could have made that period longer. And so that can affect our answer. And so let's put down 2 pi thirds, all the values which could get us back to that same terminal side of 2 pi thirds. And so I know adding 2 pi to 2 pi thirds, that would just get me a full revolution from that terminal side. So I'm going to put here plus 2 pi times k. K is an integer. So that funky E is contained in, that funky Z means integer. And then we're going to do the same thing for the 4 pi thirds. And then we're going to solve for theta. So we also have 2 theta is equal to 4 pi thirds. But if I add a multiple of 2 pi to that, I get to the same terminal side. So plus 2 pi k. So first thing you want to do is you want to solve for theta. So I could solve for theta in that first equation, 2 theta equals 2 pi thirds plus 2 pi k. My dividing by 2, I notice I have fractions in there. So to me, it would be easier if I just multiply both sides by 1/2. Let's distribute the 1/2 on the one side and simplify. So we get theta here is equal to, so if I multiply 1/2 to 2 pi thirds, notice our 2's would cancel, leaving us with just pi thirds. When I multiply the 1/2 to that 2 pi k, again, my 2 would cancel, and this would give me plus a pi k. So in a minute, I'm going to choose values for k, integers, to see which values, when I plug in my integers for k, would give me theta between 0 and 2 pi. If it had asked for all solutions, I would just leave it like this. But it's wanting just solutions between 0 and 2 pi. So I'm going to go to that second equation, 2 theta equals 4 pi thirds plus 2 pi k, and I'm going to multiply both sides by 1/2. So that would give me theta here is equal to, so distributing the 1/2 to that 4 pi thirds, 2 goes into 4 twice, so that would give me 2 pi thirds plus 1/2 times 2 pi k, again, the 2's cancel, giving us pi k. So we want to find all the angles that would work between 0 and 2 pi. And so let's just start giving values. Let k be 0. So if k is 0, I plug in 0 for k here. Well, pi times 0 is 0, and that would just leave me that theta is pi thirds. So there's one answer. Pi thirds is between 0 and 2 pi. Now let's look at when k is 1. If k is 1, I have pi thirds plus pi, because 1 times pi is pi. So 1/3, or pi thirds plus pi, getting a common denominator. So pi thirds plus 3 pi thirds is 4 pi thirds. And if theta is 4 pi thirds does fall in our interval. So 4 pi thirds is another answer that would work. So you're going to keep doing this, keep choosing values for k that are integers until we get out of the set between 0 and 2 pi. So if k is 2, well, I'm just reasoning, 2 times pi is 2 pi. And if I add pi thirds to 2 pi, that's going to get me outside of the interval between 0 and 2 pi. And so k equals 2 doesn't work. That doesn't give me another answer. You should maybe check when k is -1. So getting negative integers. But I notice if I plug in -1 here for k, that's negative pi, or -3 pi over 3. And -3 pi over 3 plus a pi thirds is -2 pi over 3, which doesn't fall between 0 and 2 pi. So that one also doesn't work. So doing the same thing here where k is equal to 0, plugging it into this second equation that has k in it. Well, if k equals 0, then we get 2 pi thirds, which is between 0 and 2 pi. And now choose k equal 1. So that gives me pi plus 2 pi thirds. So 3 pi thirds plus 2 pi thirds is 5 pi thirds. 5 pi thirds still falls in between 0 and 2 pi. So we got 4 solutions that work for that equation. So if the argument, that angle, is not just theta, and there's coefficients in there, or we're summing values in there in that argument, then we have to do this little trick in here where we have to put in this 2 pi k. That would get us up to the same angle, at least for all our trig functions except for tangent and cotangent. So this next equation, I notice my argument is not just theta. I have 5 thetas plus pi over 18. So the equation is sine of 5 theta plus pi 18ths is equal to 1. So if the argument is just not theta, let's choose some value to equal that. So let a equal this 5 theta plus pi over 18. And so looking now at when is sine of a equal to 1. Well, between 0 and 2 pi, there's only one value, a sine, that gives me back 1. And that is at pi halves. So a is equal to pi halves. Okay, so, but I know that doing a full revolution from pi halves would get me the same terminal side. So I can add plus 2 pi, or any multiple of 2 pi, so 2 pi k. So I know A is pi halves plus 2 pi k. But A is not what we're looking for. We're looking for theta. And we know that theta, we know that phi theta plus pi over 18 is A, is equal to this pi halves plus 2 pi k. So we want to isolate theta here. So first thing we would do is let's subtract pi 18ths on both sides. So we get 5 theta is equal to, well, common denominator would be 18. So 9 pi 18ths minus 1 pi 18ths. So 9 minus 1. So this is 8 pi 18ths plus 2 pi k. So we can divide both sides by, let's reduce that first. 8 and 18 both have a 2 in common. And so 2 goes in there 4 times. So we have a 4 pi in the numerator, and 2 goes into 18 9 times. So right now we have 5 theta equals 4 pi ninths plus 2 pi k. So let's multiply both sides by 1/5 to get theta by itself. So 1/5 times 5 theta is equal to, distributing our 1/5. So 4 pi over 9 times 1/5 is 4 pi over 45 plus 1/5 times 2 pi k. So this gives me 2 pi k over 5. So in order, we're going to just start plugging in values for k. It would be easier, it's going to be easier if we had a common denominator. And so let's multiply that second fraction, 2 pi k over 5, by 9 over 9. That way we don't have to get a common denominator each time. We're plugging in values for k. So this is 4 pi plus 18 pi k all over 45. So k is equal to 0. So if k is equal to 0, I have 4 pi plus 0. So that's 4 pi all over 45. So 4 pi over 45, that is falling in between 0 and 2 pi. So now choose k equal 1. So if I plug in 1 for k up here, that would give me 18 pi plus 4 pi. That's 22 pi over 45, which still falls inside that interval. So now choosing k equal 1. Oh, I did that. K equal 2. So here, 2 times 18 pi. 2 times 18 is 36. 36 plus 4 pi is 40 pi all over 45. And then if I can see that it's going to be too big, but if, let's just show it. If we do k equals 3, 3 times 18 is 54. So that would give me 54 pi plus 4 pi is 58 pi. 58 pi, maybe it's not too big, all over 45. That's not too big. So that actually works too. I know it's not going to work when that numerator is above 90 pi. So we got to keep going. So k equals 4. That's going to get me up to 72. Right, 4 times 18 is 72. So that's 72 pi, just for this piece, plus a 4 pi, 72 plus 4 is 76 pi, all over 45. K equals 5, that's the one that's going to be too big. But let's just show it. So 5 times 18 is 90. So that is 90 pi plus 4 pi is 94 pi, all over 45. But this is not contained in the interval between 0 and 2 pi. So we would not use that answer. And we don't have to go further with the integers greater than 5, because they would all fall out of that interval between 0 and 2 pi. We should look at, again, sometimes the negative value could get us a value that falls in that interval, negative integer. But I see that if I plug a -1, that's negative 18 pi. Negative 18 pi plus 4 pi, that's negative 14 pi, all over 45, which again, that is the negative value, so it can't fall in the interval between 0 and 2 pi. And so we wouldn't look at this answer either. So there are 4 answers that work. Actually, that's 5. There are 5 answers that work, which we have boxed here. 4 pi over 45, 22 pi over 45, 40 pi over 45, 58 pi over 45, and 76 pi over 45 should satisfy this equation. So looking at one more example, we have sine of theta over 2 equals √3/3. This time, the direction says give the general formula for all solutions. So all solutions are going to be could be outside of 0 and 2 pi, and then it wants us to list 6 of the solutions. So we would approach this the same way, because our argument is not just theta. Let's just choose that A to be theta over 2. And so now let's just look at when is sine of A equal √3 over. This should be actually √3/2. Okay, so there is a value of A that gives us back √3/2. That's 60 degrees or pi thirds. So A equals pi thirds. But a full revolution from pi thirds, or multiple revolutions from pi thirds. So we can add plus 2 pi k here. So also, though, there's another value of A for sine that gives us back positive √3/2. And that is, sine is also positive in the second quadrant. And so thinking about pi thirds as our reference angle in that second quadrant, and thinking about what angle from standard position to that terminal side would give us the reference angle of pi thirds is 2 pi thirds. So we can say that A is also equal to 2 pi thirds plus 2 pi k. But we don't want A, we want theta. And so theta over 2 is equal to these pi thirds plus 2 pi k. Theta over 2 is equal to 2 pi thirds plus 2 pi k. So solve for theta. We can multiply both sides by 2. So 2 times theta over 2 is just theta, is equal to, distribute your 2 on the other side. So 2 pi thirds plus 4 pi k. And theta is equal to, distributing our 2 here, same thing. 2 times 2 pi thirds is 4 pi thirds. Plus 2 times 2 pi k is 4 pi k. So these are the general solutions or general formulas for the solution. But I wanted us to list 6 solutions. And so to me, it's easier if I'm going to have to start plugging in values for k so I don't have to get a common denominator each time, is to multiply this by the fancy one to get that common denominator. So we can say, well, theta then is equal to 2 pi, multiplying 4 pi k over, by 3 over 3 is plus 12 pi k all over 3. So we could use that as our general formula also. Or 4 pi plus 3 times 4 pi k is 12 pi k all over 3. So again, that could be we can write that as our general solution. And then to list values, just start choosing integers for k. So if k was 0, we got 2 solutions here. We got 2 pi thirds and 4 pi thirds. If k is equal to 1, we got 2 other solutions. So we got 12 pi plus 2 pi, that's 14 pi. So 14 pi thirds. Okay, 1 again. So that's 12 pi plus 4 pi is 16 pi thirds. And it didn't tell me what range they wanted it in, so I could choose any value for k that is an integer and do this. But I'm just gonna do positive ones. So if I put in 2 there for k, well, that gives me 2 times 12 pi is 24 pi. 24 pi plus that 2 pi, so that would be 26 pi thirds. Same idea, 2 for k, so that's 24 pi plus 4 pi, that's 28 pi over 3. So here's 6 solutions of the infinite number of solutions that we could have when our angle doesn't have to be between 0 and 2 pi.